Hi everyone, my name is Mohan. I'm going to be presenting on a laboratory scale 2-axis tracking heliostat apparatus or solar concentrator for the Nanoscientific Symposium. So my name is Mohan. I'm a rising junior at the Cambridge Ringe Latin School in Massachusetts, and I'm working with Chris Stokes, who's a laboratory engineer at the Rowland Institute at Harvard, and also Dr. Ye Tao, who's a principal investigator at the Rowland Institute at Harvard. A bit of background about the project. My work is part of Project Mirror Reflection, which is a geoengineering framework. So basically, as the climate changes, planetary ecological systems and humanity face a series of threats. And one of the most urgent and severe is extreme heat and thermal changes due to energy imbalances in the environment. So Project Mirror Reflection is a new geoengineering framework which seeks to create versatile mirror-based infrastructure to mitigate these temperature extremes and enable a recovery of biodiversity and biomass affected by climate change. So what I'm doing for this project is building and designing a small-scale heliostat apparatus with active sun tracking capabilities. Basically what that means is a device that reflects incoming sunlight using multiple mirrors and concentrates it to a focal point. For context, here are some other examples of heliostat apparatus and their uses. Obviously, they're used for producing solar power, generating electricity, solar cooking, or heating water. So the overall idea for our project and the goal is to create a small-scale heliostat apparatus that focuses light into a reaction vacuum chamber to sustainably calcinate calcium carbonate in clamshells. And this process enables an efficient capture of pure CO2 off gas. So this is the vacuum chamber I'm talking about, where the reaction will take place, and we'll be burning the clamshells in this area, and the light will be shown in through this glass pane. And the device is also intended to be a model for larger scale heliostat apparatus. And finally, we plan to make the design open source, modular, and affordable, so it can be created by all types of people around the world and inspire an interest in solar concentrators and solutions for climate change. So why is our approach unique? Most designs use one large mirror or a set of large mirrors to concentrate light, but we're using a flat plane concentrator approach, which uses multiple mirrors on a flat surface. And that means that our design or our approach is less susceptible to strong winds and is also lower in construction requirements because of its smaller scale and weight. And it also means our design is versatile, so it can be easily implemented on a small scale in homes or on a larger scale in the future. So overall, what we're building is an array of 80 2.5-inch mirrors in a 1 meter squared rectangular grid. And these mirrors are mounted on universally articulated, individually angled 3D printed blocks. And the system uses a microcontroller and 2 precise motors to angle the mirror system on 2 axes, maintaining a desired stationary focal point as the sun moves across the sky. We're basing the design on a heliostat apparatus patent, and as well as the concentrator report. And we hope to achieve a peak power of 1 kilowatt under optimal conditions, and a maximum operating temperature of 900 degrees Celsius. And this would be in a 3-inch focal point. Now let's dive into the overall engineering design. So we have multiple mirrors arranged in a rectangular array to a pegboard. I'm going to be showing you a model 2x2 mirror array we have so far, but in the future we'll be building something bigger. Anyway, so we have multiple mirrors attached to a pegboard, and each mirror is attached to rods with 2 flexible joints. And the rods and joints are attached on 2 levels. On the bottom, or level 1, they fit into a rigid support layer, and on the top, level 2, they're attached together with dowels into a grid to form an adjustment layer. So in this diagram, this flat surface is the mirror, here's the dowel, here's the support layer, and the movement or adjustment layer. So as the motor moves the top adjustment layer in any direction, all of the mirrors move or change angle together, maintaining that stationary focal point as the sun moves throughout the sky. Here you can see some photos of our prototype. So let's dive into the universal joints. So the universal joints are going to be 3D printed. This is their design. And there were considerations between a ball and a socket joint, or a flexible coupling, or this current design, which uses these little knobs to create the articulation. And these universal joints are basically going to be on both levels of the mechanism, connecting the dowel to the adjustment layers. And this will allow the system to move or angle freely on the X and Y axes. So now let's talk about the focal point. So the mirrors are attached to the top of the dowel with a mounting block, which is at a certain calculated angle. And this angle is different for every single mirror. So the angle is calibrated such that when the sun is at noon, the focal point, the sun is reflected to a focal point 1 foot in front of the mirror array and about 5 feet high. And that's just so that the light can shine into the reactor in the lab when the concentrator is on the floor. So in this case, the mirrors on one axis both tilt towards the center, and on the other axis, they all tilt forward to reflect the light to a focal point. You can see the two side views over here. Here you can see the mounting pieces, and here's that actual angled block that I'm talking about. And so I have a spreadsheet and also a Python script to calculate the angle of the mirrors on two axes, and it takes into account the dimensions of the mirror and your desired focal point to give you the angles. And you can also fine-tune the angles using small screws, and we have a projector system to calibrate each mirror's position individually. So now you might be wondering, how does this system get moved on two axes by the stepper motors? So we have two stepper motors. Stepper motors are basically motors that can precisely control movement. They're often used in 3D printers. And these stepper motors adjust the angle of the mirror on two axes. So one stepper motor controls each axis, and a lever or a hinged arm allows the motors to push and pull the adjustment layer this way to adjust the mirror's angles, and then a slider joint here enables two-axis movement. And all of the mirrors move together to maintain this focal point. For the electronics, we're using a microcontroller, the stepper motors, a real-time clock to keep track of the time, and two end stops to be able to home the system and basically establish a known position each time the program is run. So now let's dive into the code. So the sun moves across the sky in an arc shape, and its position is defined by azimuth and elevation angles. Azimuth is the degrees from north, and elevation is the angle above the horizon. So the code uses calculations from the National Oceanic and Atmospheric Administration about the sun's position. And it basically gives you the azimuth and elevation angles based on latitude, longitude, date, and time. So the code, first it takes your time and location and calculates the elevation and azimuth angles with the calculations I just mentioned. And then it converts these spherical coordinates, elevation and azimuth are in the spherical coordinate system, to Cartesian coordinates, x, y, z, to be able to calculate the angle of the mirrors on the x and y axes. So it calculates the desired mirror angle, and then it translates that angle to the angle the stepper motor needs to move to, and also to the steps, or like instructions, the stepper motor needs to take. And then the code moves the motors to this desired position and repeats it many times to adjust the mirror angle and maintain the constant focal point as the sun moves across the sky. So all of this code and mechanical system come together to create the device you can see here. So far, we have conducted some testing of the 2x2 system. Here you can see the concentrator and the 4 mirrors set on the table, and there's a projector shining light down from the ceiling. And you can see the mirrors are successfully focusing that light into a focal point on the cardboard over here. And indeed the focal point stays together as the concentrator or the projector is moved. So this means that the system is working. Going forward, we're going to scale it up to more mirrors, 5 by 5 and 9 by 9. We'll conduct testing with the vacuum chamber and the reactor. We'll collect data on the power output, temperature, and CO2 capture. And we could also experiment with other optimizations, for example, the shape and arrangement of the mirrors. Thank you for listening to the presentation. Let me know if you have any questions or feedback. Thank you.